Welcome to Renaissance Videos, and my name is Friedrich, and this is the second video along the lines of the selfish, unthankful circuit, or the loving, giving path. So in this demonstration, we're just showing a bigger motor doing the same thing, and I may say another word here or two here. The first thing we want to mention is this is our four dual pole energizer kit, which we sell on our website. And what we're going to show today is the intermediate level of running this motor. So again, we've already talked about in the last video the idea of the closed loop circuit. So here we have two closed loops, the battery across the motor. This is a standard motor. And then there's also another closed loop, a diode, or a suppressor snubber system, flyback diode, and we're losing all the potential energy in this configuration as well as this configuration. So the basic way of running this motor that we're running here, or any pulse motor, is to redirect the diode to another battery or another load. For instance, we use these LEDs or other types of resistive loads. So we've opened the loop here. So we've made it unselfish, as I've said. We've made it a loving, giving path. So now this energy is not consumed upon itself and wasted, as we normally do in all of our electronics. Now we're actually charging this battery pretty much at the rate of discharging this battery. So this is the basic level of running these motors. But now we're going to add another level. Before we do that, I'm going to show you again this basic system. Here's another closed loop across a bulb, or we can put an inductor there or a motor there. And so all the energy is wasted by closing the loop. The bulb, as we showed in the last video, is not consuming any energy, really. But the battery is discharging itself when it's in a closed loop. So when we actually open the loop a little bit more here, and we have a second battery, we can actually charge this battery while this bulb is running. Now pay attention, somebody didn't pay attention to the last video, they skipped through it. Well, this battery, we're gonna make twice the voltage. So say this is a 24 volt battery bank, two 12 volt batteries. This is what we actually have here. Two 12 volt batteries in series makes 24 volts. Now we're going to put two 12 volt batteries in parallel for 12 volts. So there's a potential difference across here and here of 12 volts. So this bulb will run just like over here as this power is discharged across this battery, because there is a closed loop here. This bulb will run though for free, and this battery will charge up minus the losses in the closing of the loop here. So you can actually run this circuit quite a bit longer than running this circuit with the same amount of power. Quite a bit. We showed in our last convention this demonstration where a bulb would have run out in an hour and a half to 2 hours. It ran from 8 o'clock in the morning when we started the meeting to 6 o'clock at night before this battery, which was totally discharged here, these two batteries, and this was fully, well, almost fully charged. And so what we're going to do with here is we're going to do the same thing with this motor system. We're going to put the motor in series with these two batteries. So again, we've shown this. There's links to these PDFs, so don't worry if you can't see it, all the writing and all that. So I want to just read a verse here, because no man can receive anything unless it is given from heaven, said John the Baptist. It is more blessed to give than to receive. And I want that to be included in this analogy because it's very important. We're talking about sharing the energy. So we've talked about this one right here, sharing this energy here to another path. Now we're going to go from here to here in this system. So now we've put the motor here, and we're going to have two open path systems. They're semi-open because there's still a loop. It's just not a regular loop. So now we're going to run the motor through these two potentials here. But I'll show you a better diagram of actually how we're going to do it with this motor. So what we have here is the two negatives again connected. Just as we had in the bulb. And then we're going to run the motor on between the two positives. Note that the normally negative connection here is going to the positive of the charging battery, which is over here. So I've got a mess of wires here. People complain about them, but it's the only way I can show it with all the wires here, so people don't doubt what I'm doing. So we have number one battery, 24 volts. So these batteries here are in series. This negative tied to this positive one. And what we have is the motor positive, right, up here, coming from the coils, all the way around to this connection here. So there's the primary positive. And then we have the negative coming across down to here, which is battery 1 to battery 2. So these are in parallel. And then the other end, normally negative terminal on the motor, which we have in black, goes all the way across to this positive terminal. Now it's a positive terminal because we're splitting the positives. We're between two positives of different potentials. Again, this is two 12-volt batteries for 12 volts. This is two 12-volt batteries for 24 volts. So the difference between this is 12 volts. So now we have a couple other things here we haven't shown before in any videos. We have a capacitor bank over here, and this is across the charging output. So battery number 3, we've got two golf cart batteries. These are 25 amp hour batteries, 12 volts, two 6 volts in series. These are 35 amp hour batteries. It should make it easier to see the batteries because they're smaller here. We're only going to run this around 10 to 15 amps, so we're good to go here. So again, this battery is going to charge at the rate that this is discharging. This battery is also going to charge as we used to charge in the other circuit. So battery number 3 is represented here in this simple circuit. Remember, these batteries are in series with each other, positive to negative. So between here and here is 24 volts if these are 12-volt batteries. And I can actually charge up 300 volts of batteries if this is 12 volts. So on this circuit, that other battery is still there. but it's in this location. What this gives us is the ability to swap these battery banks around while we take a load off of this continuously and have a mechanical load in the motor. So again, the motor can run just like a regular motor, and we can regulate it here. We have a big rheostat potentiometer to adjust the speed, and I have a bulb here that's going to also be on this trigger, which is the base of each of the transistors. And so there's a trigger coil. One of the wires here out of the 32 wires, because there's 8 on each coil, one of the wires is a trigger coil, and that's turning on all the transistors. And then we have diodes coming out from each coil to the positive terminal of that capacitor bank right here, and I'll bring the camera over here afterwards. And then we have the negative terminal is shared right here. Pay attention to that. The negative terminal from the capacitor bank is connected to the primary positive terminal. And you can see our other videos to understand that and look at the circuit diagram. There's an SCR here that is discharging this capacitor into the battery. And that allows the voltage over this battery to be about 1 volt difference. So it's a gentler charge to this battery than normally we have a big spike coming through here. So the cap kind of absorbs that, and it changes the energy from a negative energy to a positive energy, which is what we want to do in this situation. Now the inverter also has its own set of capacitors, and we're going to plug a light bulb into that. So, so this is the intermediate level of running this. And I want to read, the advanced level is something I showed in the other video, but I wanted to read another verse. For God, who commanded the light to shine out of darkness, has shined in our hearts to give the light of the knowledge of the glory of God in the face of Jesus Christ. 2 Corinthians 4:6. And now this process here, I've shared enough in my last video to actually reveal what it is. Some people have figured it out, and but this is a very difficult thing to add. Now we add this in series. Now I don't show the capacitor here and the SCR like we do over here. And this was, you just have to look at this in the same way as this. We can do the switching on either side. But anyway, so this part right here is no different than this. You just have to imagine this over here. So this is what we call the 0.0 voltage process. And so we add that in series with the charging battery. And now we actually run another load here while this actually receives some energy as well. And this battery number 1 now can actually charge up and remain charged. We can make it stay the same, charge up, or discharge depending on our settings here and our loads. And this requires a lot of balancing, and actually on this very motor I blew out some circuits because I had too much power resulting in here, and it blew out my load and it blew out my circuitry. So in this video I'm not going to attempt to show that right now. We showed that at our meeting in Goshen, Indiana, the last 2 conventions. Anyway, this represents infinite energy. It represents 0 voltage across the terminals. I show positive, negative, but they're actually 0. 0 AC and 0 DC. And we can multiply this process out as many times as we want. And so that is really incredible. The only downfall of this kind of system is we have a lot of batteries. And we can do other circuits to lessen the batteries, but this is the easiest way right now to work it. So anyway, we're going to run this. So what we have also is these generator coils. Every other coil is a generator coil. And it's just one wire, 18 gauge. I've got these 100-watt LEDs. When we run this at 24 volts, these come on really bright. But right now we're just going to run these at a lower level, the 12-volt level, and make this all simplified. This is not something that I'm trying to prove to you guys right now. You know, thousands of people have made these motors, and now they can try this process for themselves, which people are starting to do. And that should change the world fairly rapidly, because this is giving you 3 outputs for 1 input. 2 outputs wasn't enough for a lot of people. It wasn't enough for me, but for a lot of people they wanted more power. So we've shown how to do 3 outputs now for 1 input, and in fact these 2 battery banks can virtually rotate around while we now have the power here on the shaft, which is being used partly by these generator coils and the motor. So we're going to run around probably about 11 volts here, because these batteries are slightly discharged, and 10 amps. So we're only talking about a little over 100 watts. So in fact, I should probably get a 100-watt light bulb here rather than the 300-watt light bulb that I have there. But we have a heater here that's a 200-watt heater, and maybe I can find really quick without stopping the camera a bulb here that is 100 watts. I do happen to have a 100-watt bulb. Good. So you can see I've got 2 cameras here, so I want to show both cameras. And this one you'll see here. So you can see this battery is quite discharged, 1183. And you can see going down, that's a pretty bright light. And what we're going to do then is replace this. I didn't know until I got it set up how much amperage I was going to push in the input. So let's run this one. It's a lot gentler, a lot less. So this is about the similar power level. Now we'll let that kind of stabilize here, and then what we have here is a 100-watt, I think, 300 ohm 100-watt rheostat, and a 25-watt 20-watt actually 12-volt lamp. So we're going to run that. Now we could add more resistances here and do different things. So I've got the trigger wire, as we call it, over here, going through these. These are in parallel with each other, and this is another negative energy, free energy process here in the trigger coil. So there's all sorts of interesting arrangements that we can do series and parallel on the trigger coil. And then I have just a circuit breaker, 200 amp right here. So I think that explains everything. There's no hidden things here. This is all straightforward. There's nothing exotic beyond what we're doing, the arrangement of the batteries to the motor. This is all, like I've said, we've taken a brushless fan and converted it right out of the box with, not even adding parts to it, just removing some parts, adding some wires to charge a battery. So we can do this with conventional motors. The design that we have here is a better geometry, and the generator coils where I place them are additive to the system. So, you know, there are some benefits, of course. That's why we're selling this rather than other motors. We are selling the fan kits as well. But anyway, what we're going to do is get this running now. And I'll just turn it on. I'm going to turn it on. I've got an amp meter here. And we'll get this on to start. Put it in DC. It's going to be upside down unless I can maneuver it here. I'm not sure if the camera will see this very well, but I'll put it there anyway. Yeah. No, I got to zero it. So, let's make sure our voltmeters don't time out on us so that we lose that. And so again, what we have is a bulb here plugged into this inverter. This is just a car adapter, and then again, this is an SCR. It's triggered by a diode. Make sure nothing's touching there. And I've clamped the inverter to the negative terminal there. So let's get started here. And so we're at 1224 on the charging bank, 24.5. So we've it's like 12.2 on each individual battery, 12.25 maybe. And then I'm going to turn this one on to show you the capacitor, the voltage on the capacitor. It's 1137, 1136. So what we're going to do is, so that right now is, these are leaky caps a little bit, so they've gone down a little bit. I just ran it briefly, and so you know you can see some of the voltages stabilizing. So what we're going to do is just get this started here, and we can spin it either way with the trigger coil. So you're going to hear a thump when I connect it. Listen for that ding. So that's, you can see there was no great power drainage when I did that, but that represents a very interesting thing to investigate. So we just give this one is not self-starting. We have to actually turn it. So you can see here the trigger is producing some energy here that we're wasting, and all these resistors are also wasting the energy. So now I'm going to turn this up, get this up to speed here, and I'm not sure what the amps are, about 10 amps. See if we can adjust that. And I think we're going to just keep it at 10 amps. Anyway, let's look at some voltages. So again, we've got this light on here at partial brightness. We're not talking about, you know, megawatts here, but we are charging the charging bank here, and of course we're discharging. So we've got 10 volts now. We're running the motor at 10 volts. Between 13 volts and 23 volts is 10 volts, 10 amps. So this is 100 watts. Now we're charging the other battery bank. And so what I'm going to do is look at the voltage on the capacitor to show you. .91 over 11.93, so it's about 1 volt difference on here. And I can show you. but this is the same voltage. So 12 volts approximately. So it's charging up this battery bank. And now it would be best to actually charge the battery bank and not try and run the load off of it, but how many battery banks do people want? You know, like, we got to come to some kind of place where we say we got to stop trying to be so idealistic, which would mean, you know, we can only have so many battery banks. Okay, so those are transferring the energy, so to speak. I don't really believe it's actually transferring, but that's the way people look at it. So now I'm going to turn on an inverter, the 100-watt bulb, and you can see if it's not too bright there, the voltage, 1178. So it is, you know, of course, discharging the battery. It's balancing out from where it was, more or less 100 watts. You know, we haven't necessarily run it at the sweet spot here. This is just, you know, just to give you the overview here rather than trying to prove something the most effective way. For me, I'm not so concerned because I can add, you know, the box. I can do other things. I can multiply this process even right here out many, many times. And so I can actually make as much energy as I want, even with this system. You can all do this too. I just have to think a little bit what's involved over here, which I've just shown, and what was involved in the primary thing was really implied here if you had paid attention. But most people never really got that. So what's involved in the other things that we're doing, just pay attention to what we're doing and then you'll figure it out. So we can, you know, so I'm not so concerned about the sweet spot so much here because there's quite a bit of energy here. There's 3 outputs for an input, 1 input, and it's just a matter of you know, arranging your batteries. I mean, that's really all this is. So it's fun. Now we're running these, they're still not too hot. You know, if we're going to run these anymore, we need to put some heat sinks on. So we have some power here. Now these are 100-watt bulbs, and they're running probably not even, you know, 25%. There's still quite a bit. So when we get this all tuned, we're looking at 100 watts of mechanical load. We're looking at 100 watts of charging, 100 watts of discharging, another 100 watts of charging, and of course we're running the bulb right there. So we have, you know, a very easy, verifiable demonstration of what people might call over unity. People define that differently. It doesn't really matter to me what you use with your, how you define your words. To me, at the end of the day, it's just a matter of what you want to do, you know, and call it what you wish. You know, I'm not here to redefine words. So anyway, I think that's really what I wanted to show today, and I think that covers it. Any questions? I'm sure I'll get them on the YouTube channel here, and go easy with the emails and that. We are making this open source, this information. Many have done that over the years, and I'm grateful to all that have contributed to this kind of technology. You know, it's not been quite open source over the years. This process right here has been shown here and there. I'm going to mention John Snell, and haven't heard from him in a long time. He brought this out years ago in a little bit different way on KeelyNet. Of course, going way back to Tesla, brought these processes out in slightly different ways. And then there's many others who we're doing the same sort of thing here. I'm not trying to claim that I invented any of this. I mean, I've invented a few things, but I'm here just to try and help you understand this technology and use it, you know. But I'm also going to warn you to be safe, and that's a big desire of mine, agenda of mine, is for your health. I'm for your health, and so I want you to be safe, and that's one reason why the box thing isn't quite disclosed yet until we do the whole science and present that. It's just a little bit difficult to explain that whole thing. Anyway, I hope you've enjoyed this video, and remember, with Renaissance, going green saves you money. I don't know if you can see that in the video or not, but and let's take a look one more time with the cameras here. I'm going to show everything running. Actually, this is backwards. Let's go like, you can see the negative signs. So yeah, it's still 10 amps. And what I'm going to do now is bring the camera around so you can see there's no monkey business going on here. So you can see the battery's pretty much holding out. The big battery here is pretty much holding out. It's holding its charge with that 100-watt bulb on it. We can look at that as well with the amp meter to see. Hold on. So we can look at the amps here, 10 amps roughly from the going into the inverter. And of course, I'm not going to try and turn that over, it's too hot, it'll start melting things down. So let's look around here. I'm supposed to hold this to my chin. So you can see there's no wires going anywhere else or anything like that. So there's that. Now I'm going to take my second camera because I don't know which camera is going to turn out better. And I'm going to place it back here. So again, we've got these voltages here. Yeah, here. And I want you to see it connected over here, this terminal. You can see that really, I can get this around. See, look, oops, hold on. We've got to do this bit. We've got AC. Here. Let's go right here. See, we only have 6 amps represented, 6.74 coming into the battery. But it's the way it's being pulsed. Now, if you look right here, isn't that interesting? Hold on, put that backwards. You got 0 practically right there. And then from here to there, like let's try and see if we can get across this. We only have like 5, 6 amps. So different places gives you different results or different readings. So then again, here we have the negative terminals coming off here, going around to the charging positive, and then we've got the coil coming right here to the primary positive, and then you can see these two are in series, and these two negatives are connected together. And I'm going to take the other camera right now and run this the same thing that I just showed, just so that people can really see this. So I think I'm going to use the other camera. So let's take this camera again. We can see it's just slightly discharging. It may be just still coming to balance. But let's look at these voltage again. So we have 0 volts here, right? On the cap. But what do we have right here? On the negative side, we only have 2.4 amps. On this side, hold on, let me get right over here. On this side, 2.4 amps. If we can get across this guy, 2.4, and yet we have 6 amps on this side, and about 7 amps between these batteries. So then, of course, as I showed here already, we've got 10 amps coming from the battery to the inverter, the 12-volt inverter, which has its losses. You know, you got about 20% at least. Cheap old inverter, it's probably like 25-30% losses there. So I apologize for the shakiness. I bought this expensive camera thinking that the GoPro, and it's not as good as I thought it was. It's action camera and there's no stabilization in it, unlike my other camera. So I do apologize for any shakiness. Maybe Google can do the anti-shake thing for me again. So what we should do actually is turn this off and then let these voltage stabilize a bit. And then let you see them for a bit. So let's turn off the inverter, of course, because we want to obviously not drain the battery while we're not running the motor. But I want you to see at least these voltages stabilize, and again, that there's no monkey business. There again, you see no amps, of course. No amps. So it's interesting, you know, the SCR and the way it's working. Like it says, 1 volt over top of the battery, the charging battery, and so it's a great charging system. I mean, you can regulate that with transistors or MOSFETs as you please. You can the SCR is a nice switching device that is easier to use than other semiconducttors, and it's not as controllable as I got one screw here loose. But anyway, I think that pretty much covers it. What we can do here with this motor system again is heat sink this a little bit better for higher power. We're starting to use water cooling in our systems, so we can actually cool the semiconductors. Either we can use MOSFETs or transistors here, and if we water cool them, then we can push them to their maximum. And we never really want to push them that far because the pulsing in the system is quite an avalanche current. So you have to be aware. You don't want to go too close to the limit. You want to run in the safe operating zone of the devices, which means you have to look at the temperature. So we're cooling on both sides of the transistors and the MOSFETs now, and so we could actually push this motor. If you're going to run this at 100 volts or higher, you could get up to you know, 4,000 watt system. Let me see here. If we take each coil here can do about 15 amps before you would have to start cooling the coils and like blowing some air through it or something. So 15 amps each, you know, times 4, it's giving you 60 amps. Say if we were going to do 100 volts, we're looking at 6,000 watts. 60 amps. So each board then could do 15 amps, which is easy for those transistors to do actually. So what we were doing here was only 10 amps. So we were only running them very, very lightly. We don't, in that case, we didn't even need a heatsink. But when we start, with this heatsink, we could do easily 1 amp per device. So that's 31 amps times, if we were doing 12 volts, we're looking at 372 watts. If we're doing, let's say 48 volts, 1400, so 1500 watts this system could run at 48 volts without even having to have a fan on it. When we start going, you know, to push, you know, 2 and 3 amps per transistor, especially at 48 volts, then we're getting closer to that higher range, and so then we're wanting to really water cool it. You know, I'd say you can go up to 2 amps with a good powered fan across a big heatsink. You could probably get up to 2 amps with that, but it's easier to do a water cooled system anyway, which we've shown. Actually, I don't know if I've shown that in video yet, but we're starting to sell it that way, the bigger motors anyways. So yeah, if you're going to go up to 3 amps, you know, so this could be, you know, 5,000 watt approximately device. Now if you go up to 200 volts, some of these transistors are rated for 200 volts, but not very many people are going to want to do 200 volts of batteries. You know, some will, and especially if you're going to do this, where you have 400 volts on the input and 200 volts charging for a voltage potential difference of 200 volts. That's a lot of batteries. So it's easier to push more amperage than multiply batteries, you know, but you got to do what you got to do. So that's basically the overview of what we're doing here. We have thinner plates here on our 4-pole and our 10-coiler system now, because the magnets are only 1/4 inch thick, and it's more affordable that way, easier to work with. And so I don't think I've shown this motor yet with those plates, but that's what we have now. And this whole system is available for assembled as well, or unassembled. And then with the assembled, we throw it in the heatsink with the all the holes drilled out and tapped. And of course we have the magnets and everything's installed, ready to go. And then we do that with the 10-coiler as well, and the little mini kits as well. So anyway, again, I hope you enjoyed this video and what we're doing here. So far I've heard some very good comments. Only one person didn't bother to watch the whole video and complained about the other video and complained about there being no schematics, but anybody who watched the video can see I showed them quite abundantly. So if you like the video, like it please, and pass it around, you know, because this is freely given. You know, and I'm not saying that you have to buy my motor. This is not an advertisement here. You can use other motors too. So this is just showing you a new thing here. That's my purpose. Hope you enjoyed it. Thank you.